at electrochemical cells and how we can calculate the EMF of the cell. Okay, now when we talk about electrochemical cells and the calculations, there are some certain things you should know as a student. One is what we call the electrode potential. Electrode potential. Remember that if I have, let's say I have this electrolytic cell, if I have the electrode inside here, the electrodes inside here, and the electrolytes, this is the electrolyte, okay? Electrolytes. This is the electrode. This is the electrolyte, okay? And then you connect this to a battery or to a cell, okay? So if you have something like this, the moment you connect this thing to a direct current, there will be a potential. The electrode and the electrolyte, there will be a voltage or a potential will be developed between this electrode and the electrolyte. So that potential that is developed between these two at the interface of the electrode, that at the interface, somewhere at the interface here, okay? At the interface, okay? At the interface. The potential that exists between the electrode and the electrolyte is what we call the electrode potential, or the voltage developed between these two interfaces is what we call the electrode potential, okay? Take note of that. Then the standard electrode potential is this same electrode potential developed but under standard conditions, okay? The standard electrode potential is this same electrode potential developed at this interface but under standard conditions. The standard conditions is a temperature of 225 degrees C or 298 Kelvin, okay? Or another standard condition is 1 atm and also 1 molar solution. So the standard conditions for it to be called a standard electrode potential is it must have a temperature of 298 Kelvin, the pressure must be 1 atm, and the concentration will be what? 1 molar. So the electrode potential developed under these standard conditions is what we call standard electrode potential. And the symbol for this one is E with a naught. E naught here, okay? While the symbol for electrode potential is just, you can say it's E, okay? So the cell potential is also an electrode potential, but this time around it's a potential, it is a difference, a potential difference between the cathode and the anode, or between the two half cells, okay? The cell potential is like a difference. It's like a difference between the two cells. The two cells, of course, we have the two cells, the oxidation half and the reduction half. The potential difference between the two cells is what we call the cell potential. So this E cell, this electrode potential or EMF of this cell, you can also call it the EMF, okay? Let's not confuse you. The EMF of the cell is also known as electromotive force, okay? Or the potential difference between the two. So the EMF or the E cell can be calculated by knowing the electrode potential for the cathode and that of the anode. So if you subtract it, whatever you have will become the what? The electrode potential of that cell, okay? Or the cell potential. Okay, now what is the importance of this cell potential? The importance is that it tells us if a reaction is feasible or spontaneous or non-spontaneous. Okay, so how do we predict the feasibility of a reaction? How do we predict the feasibility of a thermodynamic reaction? We can predict it by knowing the cell potential. Okay, if you calculate this cell potential and the value is greater than 0, or it is positive, or the value is a positive value, then the reaction is said to be feasible and spontaneous. If you calculate the E cell and it is less than 0, or that is the electrode potential is negative, then it means the reaction is non-spontaneous. It's non-spontaneous and under standard condition. Okay? So it means the reaction is non-spontaneous. Take note, non-spontaneous. So it can't just freely go on its own. A spontaneous reaction is a reaction that it doesn't need a driving force. It just goes spontaneously without any serious driving force to it. Okay, so this is how we can predict feasibility of this reaction. Now, there's an equation that we use in this electrochemical cells and calculations. There's an equation we use to calculate the electric potential or the EMF of the cell, or the cell potential, of a cell, and that equation is called the Nernst equation. It's called the Nernst equation. Okay, this Nernst equation is important because we also use it to know or predict the direction of the reaction, where the reaction will go. Okay, so this equation is giving us E equal to E naught. This is standard electrode potential, standard electrode potential minus R T over NF ln Q. Okay, R is universal gas constant, which is 8.314 joules per mole per Kelvin. Okay, so T is the temperature at standard state, which is what? 273 Kelvin. T is the temperature at standard state, 273 Kelvin. Then F is the Faraday's constant, which is 96,500 coulombs. Okay, then Q is called the reaction quotient, okay, which can be gotten separately by dividing the reduction, the value of the electric potential for the reduction, and that of the oxidation, just like these values you have here. Okay, dividing these values, reduction and what? Oxidation. So remember that at the reduction takes as the cathode, take note. Oxidation takes as what? Anode. Take note of these things we are doing here. So remember that electrolysis is a redox reaction. Because in electrolysis, oxidation and reduction are also taking place simultaneously. So electrolysis is also a redox reaction. Okay? So N is the number of electrons involved in electrolysis. For example, let me show you example. Let's say we have zinc accepted 2 electrons to become zinc ion, and then copper donated, or let's say copper, we have, let's say, 2 plus to become zinc, and then copper ion accepted 2 electrons to become copper. Let's say we have this. If you have this kind of equation now, you will see that the electrons involved for this reaction, for this redox, the electrons involved for this redox is 2 and also 2. So whenever you have something like this, you now take the N to be 2. So the number of electrons involved in this redox reaction is 2. So I will put 2 here to solve this expression. So now there is a short way we can also signify this. If we know the value of this, and this, if you plug these things here and simplify it, you are going to come up with a formula which is much more shorter than the previous one we wrote here. So if you plug in these values here, since they are constant in this equation, and solve this equation, then we can also say that E is equal to E naught minus I think is 0.0591. So if you plug in this value, this one cannot be plugged in because it can vary depending on the redox reaction. So but these three values are constant throughout the process. So if you plug them value and simplify, you have 0.0591, okay, all over this N, which is the same N here, ln Q. So this is also another form of the Nernst equation. So this is another form of the Nernst equation. So we are going to solve a simple problem using this Nernst equation. So you can be able to see how you can calculate the electric potential of a given cell. So this is just a summary of what an electrochemical cells and the calculation of an EMF of a cell looks like. Okay, so this is just a rough estimate. So you can use these ideas. Now when you start reading through your materials, you will see a lot of points you can also make on your own to add up to what we have on the video already. So we're going to solve calculation. The next thing I'm going to do is the calculation involving this Nernst equation, how you can solve problems from the Nernst equation.